This thing right here changed the world forever. One bomb, one flash, one mushroom cloud, and nothing was ever the same again. But how did we even get here? How do atomic bombs actually work? And more terrifyingly, how are they built? Part 1. How atomic bombs are made. Let's take it from the beginning. This is uranium ore. Nothing flashy, just rock laced with one of the most powerful elements on Earth. To extract it, engineers first drill a narrow shaft deep into the rock. Then they pull a reamer up through that shaft, widening the hole as it moves. This cracks the ore apart, and the loose material drops into what's called an extraction chamber, waiting to be hauled up. The work is dangerous. Rock can collapse without warning, and radiation is a constant risk. That's why the next part is handled remotely. A bulldozer, operated at a distance, loading it for processing. From here, the uranium is milled. It's crushed, chemically treated, and refined until it becomes a concentrated powder, something known in the industry as yellow cake. But yellow cake isn't what you put in a bomb. It's still mostly uranium-238, which is practically useless for a chain reaction. What matters is uranium-235. That's the isotope that can split apart and release energy. The catch is, uranium-235 makes up only 0.7% of natural uranium. The rest is inert, heavy uranium-238. So now comes enrichment, and this is where the real science begins. First, yellow cake is converted into a gas, uranium hexafluoride. Then it's fed into a centrifuge. This machine is a tall, narrow cylinder with a spinning rotor inside, driven by a motor that can reach up to 70,000 revolutions per minute. That's fast enough to generate forces thousands of times stronger than gravity. Inside this spinning vortex, the heavier uranium-238 atoms are pushed outward. The slightly lighter uranium-235 atoms stay closer to the center. It's a subtle difference, but by repeating this process across thousands of centrifuges over and over again, the concentration of uranium-235 begins to rise. First to 1%, then to 5%. But this is the low-enriched uranium used in civilian nuclear power plants. But keep going. Keep removing the uranium-238 and eventually you get to a 90% uranium-235. That is weapons grade. It's the blue zone in any simulation, where the green dots of uranium-238 almost vanish entirely. At this level of enrichment, you're no longer talking about fuel. You're talking about a bomb. And here's where it gets real. Did you know this entire process, the splitting of atoms, the chain reaction, was discovered almost by accident? Back in 1938, two German chemists, Otto Hahn and Fritz Strassmann, bombarded uranium with neutrons. Instead of getting heavier atoms, like they expected, the uranium split. They had no idea what they were looking at until Lisa Meitner, a physicist in exile, she realized they had discovered nuclear fission. One neutron splitting one atom, releasing more neutrons and a chain reaction of unbelievable energy. And as soon as scientists like Leo Szilard and Albert Einstein grasped the implications, they raced to warn the US government. If Germany figured it out first, they could win the war with a single weapon. That fear kicked off the Manhattan Project, a secret program that brought together over 130,000 people and $1 billion budget, all to build what we're about to describe. There are two types of nuclear bomb designs that have actually been used. The first is the gun-type design used in the bomb called Little Boy. The second is the implosion design used in Fat Man. Let's look at Little Boy. This bomb was built around a simple principle. Force one subcritical piece of uranium into another fast enough that they become critical, meaning a self-sustaining chain reaction starts before the bomb has a chance to blow itself apart. The design is essentially a large cannon housed inside of a 10-foot long steel casing. At the back sits a hollow uranium-235 projectile. It weighs about 84 pounds or 38.4 kilograms. At the front, there's a solid uranium-235 target, weighing roughly 56.2 pounds or 25.6 kilograms. Surrounding the projectile are 3 electric primers. When triggered, these ignite propellant charges, 4 silk bags packed with cordite, each containing about 2 pounds of it. That's military-grade smokeless powder. Once ignited, The charges accelerate the uranium projectiles down a smooth-bore gun barrel, 6.5 inches wide or 170 millimeters. The projectile is launched at 300 meters per second toward the uranium target. When the two masses collide, they form a supercritical configuration. But just putting the uranium together is not enough. You need a neutron source to kickstart the reaction. That's where the polonium-beryllium initiators come in. 4 of these initiators are mounted near the front, on a tungsten carbide plug behind the uranium target. When the two uranium masses collide, the initiators flood the material with neutrons, ensuring the chain reaction ignites at exactly the right moment. All of this is surrounded by precise fusing and arming mechanisms. There are barometric sensors on the bomb's surface. These detect altitude, and once a set threshold is reached, around 580 meters above ground, they close an internal circuit. That triggers the radar altimeters, which bounce radio waves off the ground to confirm the bomb's height, and once confirmed, the firing switch activates and the primers ignite. That's the moment everything turns. Neutrons begin slamming into uranium nuclei. Each impact causes a nucleus to deform and split. That fission releases more neutrons, which strike more nuclei, and a runaway chain reaction. All of this happens in less than a microsecond. The energy released is colossal. At the center is the fireball, about 0.36 square kilometers of total destruction. Temperatures exceed several million degrees Celsius. The blast wave expands outward, reaching a severe damage radius of 4.5 square kilometers, leveling buildings and vaporizing bodies. A wider zone, 8.7 square kilometers, suffers moderate damage, broken glass, partial collapse, radiation burns. Beyond that lies the light damage zone, up to 11 square kilometers, where heat and radiation still cause chaos and long-term health effects. Now let's turn to Fat Man. This bomb used plutonium instead of uranium. But plutonium-239 has a higher spontaneous fission rate than uranium-235, which means the gun-type method won't work. It would detonate prematurely. You need to compress it into a smaller, denser shape, faster than any explosion could do through simple impact. So the scientists turned to implosion. At the center of the Fat Man was a sphere of plutonium surrounded by layers of high explosives, arranged as lenses. These lenses weren't shaped like eyeglasses. They were three-dimensional blocks with precise curves, designed to focus the force of the blast inward, like a magnifying glass focuses sunlight. This method was first suggested by British physicist James Tuck and perfected by Hungarian-American polymath John von Neumann. His work made the timing precise, down to millionths of a second. The explosives detonate simultaneously. The outer shell explodes inward. A tamper and pusher, often made of uranium-238, compresses the plutonium core. The implosion forces the core into a supercritical state. Again, a neutron initiator ensures the reaction starts at just the right moment, and then detonation. The result was a bomb even more powerful than Little Boy, despite using less fissile material. Part 2. Why fusion bombs are even scarier. But things didn't stop there. Once we had fission bombs, scientists asked, what if we used that explosion to trigger something even bigger? That led to the creation of the hydrogen bomb, or the thermonuclear weapon. Instead of just splitting atoms, H-bombs fuse light atoms together, like hydrogen isotopes. Fusion releases even more energy than fission. But to make it happen, you need extremely high temperatures, like the kind created by a fission bomb. So fission bombs are essentially two bombs in one. First, a fission bomb explodes, then it triggers the fusion core. This two-stage process results in explosions hundreds of times more powerful than Hiroshima or Nagasaki. This resulted in the largest bomb ever detonated, the Soviet Union's Tsar Bomba. It was so powerful it cracked windows 900 kilometers away. That's the distance from New York City to Detroit. Let's admit one thing though. This isn't a Tom Cruise movie where explosions like that happen without consequences. In the real world, bombs aren't just cool visual stimuli, they have far-reaching consequences. Part 3. The ethical fallout. By the end of World War II, 2 cities were gone, over 200,000 lives were lost, and the world had entered a new age. The bomb worked, but at what cost? Since then, thousands more nuclear weapons have been built. The US and Russia alone have enough to destroy the world many times over. And today, countries like North Korea and Iran remain hotbeds of global tension, all tied to the threat of nuclear weapons. So while we now know how the bomb works, the real question is, should we have ever built it in the first place?